Can you hear us?
Yes.
Yes, great. We can start. We can wait a bit. I'm also kind of no introduction. Whatever you like. I'm kind of studied that field here before. Yeah. What do you think? We started. Okay, please. Okay, welcome everyone to have a CMSA fundamental in math physics seminar. We are very happy and delighted to have Alexander Zlokapa from MIT, and he graduated from Kitaev for his undergrad bachelor degree, and currently working at MIT, focusing on quantum computation and many things. Today he'll be speaking about very famous work on traversable wormhole dynamics on a quantum processor. Let me remind the audience, please feel free to ask during Alexander's talk, and that's directly under. So thank you.
Can I ask if the audio works?
Yeah, this works. See whether people can hear Alexander.
Chat.
Yeah.
Yes. Okay. Yes. Yeah. Thank you so much for the invitation. I'm Alexander Zlokapa. I'm a second-year PhD student at MIT, working in quantum computation with Aaron Harrow and Kitaev. This is work I began during undergrad, so it has a bunch of Caltech folks on it, as well as Leon Jaffers and David Kohlmeier. David's now, of course, at MIT, but was at Harvard at the time. So, yeah, this paper comes from two motivations. The first motivation, as somebody from quantum computation, that I really like, is trying to understand what these noisy kind of intermediate scale quantum devices can do in terms of probing interesting physics. And so here I just put a set of papers. There are many, many more papers that I didn't put on the slide, obviously. But these are papers from Michel Lugin's group, papers from the Google group, just looking at what these kind of very high-end quantum devices are able to do. And a lot of it revolves around many-body dynamics. Some of these can be classically simulated, some of them maybe not. And it's interesting, nevertheless, to ask, what does a quantum device offer that where can we learn some interesting physics by working with it? The second motivation is much more gravitational in nature. We want to know which of these quantum systems can behave in gravitational ways. And so here on the top, I just write down the SYK model. It has a long tail of history in it, of course, beginning with Sachdev and Yi proposing the SY model in the context of condensed matter. And they show this nice model that was kind of standing alone for a while in condensed matter, separate from gravity. In 2007, Hayden and Preskel proposed kind of one of the first connections, more direct connections between quantum information and gravity, looking at the Hayden-Preskel protocol, where you consider like Hawking radiation, and you have information that gets scrambled by like a random quantum circuit, is one way to think about it, and looking at how to recover this information. And so this was kind of a concrete connection between quantum information and gravitational dynamics. Then in 2010, Subir Sachdev, in 2015, Kitaev looked at the SY, or as it's called now, often the SYK model, and showed that you extract like a concrete relationship, a duality between the large N dynamics of the SYK model and this sort of AES2 spacetime. And it's exactly solvable in the large N limit. And so this is the SYK model that I showed here, with these size denoting my fermions. Here I have like a left and right system, because obviously we're going to need a left and right system when we get to a wormhole. But you can consider generically as kind of Hamiltonian, where you have these Majorana fermions coupled together in what quantum information people would call a Q local Hamiltonian. So you also have Q Majorana fermions in each term. These are not spatially connected. Instead, we just go over all possible combinations of Q Majoranas, and the coefficients in front are going to be randomly distributed. And it turns out that solving this model, like the SYK model itself, has the same symmetry group as you'd expect from the space-time mixer. And so that's kind of one of the first hints that it could be related. Then you can solve out a lot of things and show they're connected at a deeper level. This kind of this and other kinds of things prompted Maltsen and Susskind to conjecture ER equals EPR, where ER denotes the Einstein-Rosen bridge, EPR Einstein-Podolsky-Rosen entanglement pair, where they conjecture that wormholes and entanglement might have something to do with each other. This was made a bit more concrete by Susskind, I think, the following year or two. And in 2016, Gao, Jaffers, and Wall realized a kind of protocol where you could actually make wormhole traversable. Naively, wormhole is not traversable due to the average energy condition. But if you can introduce a kind of negative energy pulse in the bulk, then you can actually traverse the wormhole. They show how to do this at the level of the boundary as well, where you have this kind of quantum coupling between the left and right sides. And this quantum interaction is what produces the negative energy pulse needed to make the wormhole traversable. In 2019, Gao and Jaffers, as well as other folks like Brown et al., started to realize how you can use the SYK model explicitly, write down the full quantum circuit that does actually achieve the traversable wormhole shown in 2016, using this SYK model. And it ends up being a story of a very kind of fine-grained many-body teleportation protocol. And that's going to be the main topic of today's talk. So why is this interesting? Why should we try to put this on the quantum computer? So this comes from understanding like what quantum computers versus classical computers can do. Of course, it's very hard to prove they can do different things. This is a main topic in complexity theory. But the hope is that you can use a quantum computer to probe regimes that might not be classically accessible. And then use this to give yourself clues about parts of quantum gravity that we currently have a fuzzy understanding of. And so the regime of kind of beyond reach of classical computers is one that still lies ahead and is difficult to achieve with noisy quantum computers. Nevertheless, taking a step in this direction is very interesting. In particular, if you want to learn about gravity, traversable wormholes are a very nice example, because you can have some kind of excitation and it goes into the bulk and then comes back out. So you can ask about what it saw in the interior to some extent, and do kind of nice probes. So on the left here, that's your left. I write down the kind of space-time diagram of how the wormhole works. And we have a left and a right side. And I'll go to this in much more detail later, but for now, you can settle the fact that we throw something in on the left, it eventually comes out on the right. And on the right side, I write the quantum circuit that describes exactly these dynamics. And so this is the circuit that we're going to be running on the device. A bit of history on the experimental side, so that is a nice theoretical history. On the experimental side, this circuit that I just showed turns out to be a circuit that's very versatile and can do many different types of many-body teleportation. In the past, there have been several very nice experiments that probe some really interesting physics and show like these kind of many-body teleportation effects. It is, however, a different microscopic mechanism that we're going to look at soon with the size-winding picture. But so these experiments are kind of fall into this category of wormhole-inspired teleportation, where you have a similar circuit, but at the level of quantum information, you have a different set of dynamics happening. But I think these definitely fully satisfy motivation one of trying to probe interesting physics with a quantum computer. And it definitely takes a step towards motivation two. So hopefully today we see another step towards motivation two. So let's first understand this diagram. So here I nicely have this mapping, so you can go from negative to positive infinity. And kind of the picture is that you have a shared singularity and two mouths of two black holes. And as time goes on, these mouths are going to move further apart. At time negative t naught, we're going to insert something like the system by just like swapping something in from the boundary. As you evolve forwards in time, this is going to just fall towards the singularity. And then at t equals 0, in order to make the wormhole traversable, we're going to need to apply some kind of direct coupling between the left and the right sides. This direct coupling is going to look like just a sum of pairs of operators, like some operator on the left paired with operator on the right, summing over all operators. And in the bulk QT, this is going to look like a negative energy squeeze state. So it's going to produce this, what we call negative energy shockwave in blue. And that propagates towards the singularity. And choosing how you do this coupling can produce either a positive energy or a negative energy shockwave. We need a negative energy shockwave so that when the qubit hits the shockwave, it experiences a Shapiro time advance. And this time advance is what prevents it from falling singularity. You get a positive energy shockwave that will definitely fall in the singularity. This negative energy shockwave is enough to pull it out and bring you to the right side of the system. And so the qubit should emerge from the right side of the wormhole. In the gravity picture, or in our quantum circuit, we'll be able to assign some Majorana fermions to the right side. We should be able to read it out from those. Maybe I'll pause to see if there are any questions, because this is kind of an important story.
So the shockwave can actually keep this like this qubit out of this polarization.
Exactly. So that's the point. You can think of this negative energy shockwave as some kind of Casimir-like effect. And yeah, if you had a positive energy shockwave on the horizon, it would instead towards a singularity. So that'll actually be a nice probe we can look at as well. If we flip the sign of this energy, we should expect, a different teleportation.
What's the condition to have the shockwave? Or maybe saying that can have something more smooth.
When you say more smooth, what do you mean?
I guess it was going in lines, straight lines.
Yeah, I mean, you can, and this is going to be like, I do kind of the simplest thing. I'm going to just pair up on the boundary like these left and right Majorana fermions, but you can design this in different ways. Yeah, you can also just like if you evolve continuously under this left-right coupling, then you get like the eternal traversable wormhole. And so that kind of looks like this thing that is not just a solid shock.
Is this like very long range operator actually physical? I mean, like have them right side.
So it does require like a direct interaction with two sides. So in the boundary theory, it is just like you're smushing left and right operators together, causing an interaction. So because of these sorts of limitations, if you were to put this, like you wanted a left and right side in the same universe, and fast, could I go faster than the speed of light by doing this? The answer is no. Like the time required to actually create this negative energy shock causes you to wait longer than if you had just like done it at the speed of light. So maybe that answers the question. All right, David, if you have more comments.
Well, ordinarily, state energy wouldn't be possible because of the average knowledge, but that's violated because the interaction is not local.
Yeah. So then, what can we expect from the gravitational picture? What kinds of signals should we expect? One is a transmission peak. So let me just go back to this picture. I can play with what time I throw something in and read something out of my wormhole. And so if I throw something in earlier, I should expect it to come out earlier or later. We'll look at that later. If there's like a particular time that this kind of transmission should work, which is set by the scrambling time. And so we should expect some kind of transmission peak associated with the scrambling time of the boundary system. But at times past the scrambling time, you'll still get some kind of interference effect going on that causes a non-zero transmission signal. So then we're going to be looking for this kind of peak signature. Another signature that we can look for is one that I mentioned already, which is we require a negative energy shock wave. If we use a positive energy shock wave, we should expect weaker signal. And so this is what was touched on earlier, where if you just take the average energy condition, traversability is strictly prohibited by a censorship theorem, unless you provide this kind of direct non-local interaction between the left and right systems. And so the interaction will look like, as I said, this pair of operators hitting each other in the left and right systems. And if you change the sign of this Hamiltonian, then you will get a positive or negative energy shock wave. So that's going to allow us to check that we're only getting teleportation, we're getting more teleportation with a negative energy shock wave. Another signature we can look for is this kind of causal time ordering of signals. So because we're dealing with a physical path, we're dealing with path of space-time, we expect that if we throw something in earlier, it should come out earlier. If we throw something in later, it should come out later. And so this causal time ordering is indicative of the existence of some kind of gravitational interpretation. Whereas if you get time inverted teleportation, which is what naturally occurs in kind of teleportation through this interference effect, then you would get time, you would see like if you throw something in earlier, it actually comes out later, and vice versa. And so we're going to look at our Hamiltonian to produce this causal time ordering of signals. Another much more subtle condition might be that if you send one qubit from the left and another qubit from the right, they should meet in the middle and have some scattering event. And that should cause a bit of a delay. So we should expect our signal to come out a bit later and maybe have it a bit weaker because things won't spread out. So these are additional kinds of signatures we can look for, just solely predicted from the kind of gravity picture. So now let's try to move to the quantum picture and ask how the boundary looks like. So we're going to start with this SYK Hamiltonian. So here I have a left and right copy. And the left and right copies share the same coefficients. These J, I, J, K, Ls are both normally distributed. Oh, that's fine. Thank you. The normal distributed coefficients are the same between the two Hamiltonians, with some appropriately chosen variants. As written about by Maltasana and others, to start with this kind of eternal two-sided black hole, you pair the TFD state, thermal field bubble state. And so this is essentially designed so that you trace out one system, it looks thermal in the other system. It's just going to be basically sum over these e to minus beta en of each of the eigenstates, where this energy eigenstate corresponds to each of your Hamiltonians. Because they're the same coefficients, they also share the same spectrum, and so we can pair this up very nicely. The thermal field bubble state is gravitation development here. The SYK model and the low temperature limit. If I take the high temperature limit, this beta goes to 0, over all eigenstates uniformly. This is going to look like a bunch of EPR pairs. And so it's going to be the low temperature limit here that does not look like a bunch of EPR pairs that we are going to consider. The beginning of this kind of experiment that we're going to do requires us to swap in a qubit at time negative T naught. So first we have to get to time negative T naught. The thermal field bubble state prepares us at T equals 0, so we have to evolve there. And this U is going to denote time evolution. So you evolve to time negative T naught, and then you want to bring in your qubit. This qubit, in order to have a nice probe of the dynamics, what we're going to do is prepare an EPR pair. And this EPR pair, I put in like 1/2 of it into the wormhole. So I swapped that half into this TFD state, and then if time evolved back up. So now we're at T equals 0. And we're going to eventually check if the thing that comes out is still entangled with the other half of this EPR pair. And that check is going to happen this empty register. Now we have to apply the negative energy shock. So this coupling, as I said, is going to look like operators between the left and right applied together. So here I write that out as pairing up the Majorana fermions in this V. And we're going to apply e to the I mu B, where the sign of mu is what dictates the sign of the energy shock wave. And the strength of mu has to be correctly tuned. If it's too weak, you're not going to cause enough of a superior time advance to emerge on the right side. If it's too strong, you can enter split it. So we're going to have the correct, we're going to need the correct strength of mu and the correct sign of mu. In the literature, this is often called still like teleportation. You see that there's just like one circuit and just applied a direct interaction between the left and right sides. So why do we call this teleportation? Well, if I made a bosonic version of the protocol, I could replace this interaction by measuring out, say, the left side, and then sending those signals up to the right side to figure out what unitary to find the right side. But given that most of today's quantum computers have difficulty with these like mid-circuit measurements, we just apply the unitary as shown in this diagram across the left and right sides. But the mechanism of quantum information remains the same as it would in the teleportation. Finally, we're going to read out the qubit on the right side. So we evolve forwards to time T1, and we swap out the operators that we'd like to check if they're still entangled with the left. And we measure the mutual information with this kind of reference register P. So this mutual information between registers P and T is going to tell us if we're still entangled. Here, I'll mention one minor detail. So because these are qubits and we're trying to deal with fermions, this teleportation experiment, we pair out the fermions. So we're going to take the first two, like psi1 and psi2, and apply the teleportation protocol to those. And it's one can ask questions about the other fermions, and we will do so and what that says later. So the circuit ends up being quite versatile, as I said. It can teleport information through multiple mechanisms, including the gravitational mechanism, but also including non-gravitational ways. So there's this notion of teleportation by size, as it was written about by Brown et al. And Zami et al., or peak-size teleportation from Schuster et al. And it's an alternative mechanism that would produce high entanglement between registers P and T. But it behaves quite differently. So it's, for one, seen across many different choices of unit theory. But also it works only at high temperature. So I mentioned that if I make high temperature, this DFT stick looks like a bunch of EPR pairs. And so that's what you see in this teleportation by size mechanism. And it's symmetric across the choice of medium. So if I choose what would have been gravitationally a positive or negative energy shockwave, I will still see the signal from taking mu negative or positive, and this mechanism would be indifferent. Also, the teleportation occurs at early and late times. So you have a peak around the scrambling time, and then also at later times another signal. So this teleportation by size mechanism is the one that was realized by those earlier experiments that I showed. So it remains like an impressive demonstration of many body teleportation, but it's not the gravitational signature. Instead, the gravitational signature is one that is called size binding. After this, I'll show you like very explicitly at the level of quantum information what these two mechanisms are. But the size binding we refer to as a gravitational mechanism because it occurs in a very, it has dynamics that resemble gravity, and can also be related to objects like momentum infinity. So if you take the SYK model, for instance, you'll find that it teleports at low temperatures, this circuit. So that's the opposite of the high temperature teleportation mechanism. And it depends on the sign of this mu. So if I choose mu to be negative, it will teleport, and if I choose mu to be positive, you might just get like these other kinds of interference effects, or perhaps the teleportation by size mechanism, but you won't see teleportation by size binding. And this only peaks around the scrambling time. So we should see like a transmission peak that occurs at the scrambling time. Yes. So what exactly are these at a mathematical level? Well, teleportation by size occurs from like a time peak in the size distribution. So the size distribution is defined by taking Majorana fermion here, such as the first one, and applying it to like essentially the thermal state. This rho beta is 1 and so you decompose this Majorana on the support over all possible Majorana strings. So here when I write P, I'm imagining a string of fermions. And so psi P is a string of these Majoranas. The coefficients Cp here are generic and complex, but I can write down this basis and expand the support over all these fermions. And I can now ask about how these CPs are distributed. So the size distribution considers the magnitude of these CPs summed over everything of particular size. So here, magnitude of P I fix to L, it's going to give me this P of L distribution, where magnitude of P is the size, the number of operators that I have in this psi P string. At infinite temperature, or either sign of mu, you get teleportation by applying that interaction if the size distribution is tightly peaked around its mean. And so this is like one particular mechanism of many body teleportation, but it's not the gravitational one. Do the definitions here make sense? Because I'm going to use them repeatedly. Okay. In size winding, we change out the distribution that we're looking at. So we do the same decomposition. We ask, how does a fermion spread over operators of size magnitude P?
Can you just make sure, when you say fermion strings, where is the direction of the string is, in which space you're thinking?
By fermion string, I just mean like for example, take psi1, psi2, and ask what is the support of psi1 when I project it onto psi1, psi2. Answer the question. Yeah. So the size winding distribution leaves these complex numbers as complex, and you just sum.
Is that part of psi, or is it just the cycle of P? Is that a label?
Sorry, it's a product of size. It is a product of size. This is my shorthand. Yeah.
Okay.
Thank you.
And also summation of each of the different sides of the string.
Yes. So you sum over all possible sets of operators, and the number of fermions in the operator is going this little out. So I'm just choosing a basis, checking the support of my operator on that basis.
These are different flavors. Talking about Grossman. So are you putting them on different flavor space or different locations? How about the set of two? How's that non-zero just mentioned?
Sorry, so
These are Grossman variable.
the minor fermions, like I can still ask, I have a generic state that is this one left, and it's going to have support on some or some subset of the other string of Majoranas at a given time. Like it's a valid basis that I can write and just ask for support over this. I don't know if that answers or I misunderstood the question. Operators.
Okay, you write side square on the side.
Yeah.
The single.
Yeah. That's where it's one.
Yeah, side square.
Yeah. So the size winding distribution instead decomposes these like some of these coefficients, keeping them complex. And this allows you to ask about the phase of your winding size distribution, which we're going to look at later. And the key property required to achieve teleportation under this e to the I mu v interaction is that the phase of these two of L is linear in L. You also require that these two, the magnitude of your phase, your Q of L here phase is equal to this real P of L. So the conditions can be met partially or fully, and the better you meet these conditions, the stronger teleportation signature you should get. But you'll only see this teleportation at low temperature and at mu less than 0. So this works out analytically, and you take like the large N SYK model, and we're essentially asking about what other models might have this mechanism as well. The way to see how this teleports lies in taking these CP coefficients and decomposing them in a manner that allows you to satisfy this linear in phase and equal in magnitude to the size distribution. So I can write each CP as some phase that should be linear in the size of my operators, and some real component. So if I apply this decomposition over essentially the states generated by these operators, what I see is that applied to the TFD state, the operators on the left end up looking like operators on the right if you apply e to the I mu v. And so this kind of gives you, at the level of quantum information, a transmission mechanism that is this teleportation by size. Sorry. So alpha is just a scalar. Yeah. I'm just saying it's proportional to. Yeah. So we want to know, we've seen demonstrations of peak size teleportation in the prior experiments. Can we see some size winding teleportation in this kind of near noisy intermediate scale quantum era or NISQ era? In particular, we want to try to construct an SYK-like Hamiltonian but one that is small enough and sparse enough that a noisy intermediate scale quantum device can actually achieve kind of this teleportation by size finding. If you just kind of out of the box plug in the SYK model, you see that you get the main signatures we're looking for at n equals 10. But if you then check how big your circuit has to be, it has a few factors of 1,000,000 too many times gates for what a quantum computer can run. And so we need to find something that's much smaller, much sparser, so that we can actually evaluate on the device. And so this search for the Hamiltonian is kind of where the new material is. We want to show that we want to find a Hamiltonian that does exhibit size finding and shows the signatures that we're looking for. So here I'm first going to show you the kind of out of the box n equals 10 analysis of the full SYK model. So this is just a basic sanity check that it does show the kind of properties we were looking for, but it also tells you the sort of behavior we should expect from one of these small n gravitationally dual models. So at the n equals 10 model, we can probe the mutual information dynamics and check for the sign dependence in coupling that corresponds to the negative or positive energy shock. So if you have a negative energy shock, which I showed here in orange, you can see a peak that occurs around a particular time, which turns out to be the scrambling time. Here I showed two different types of plots. So in the left, I'm running this kind of experiment where I symmetrically inject the readout. So in my space-time diagram, it's like you choose T0 and T1 to be the same. And as you move along the x-axis here, you're injecting earlier and reading out later. And so you can see where does that produce a peak. It does indeed produce like a very distinct peak for only the negative energy. If you instead fix your injection time and sweep over all readout times, so here I fix injection time to where this peak was highest, I think it's 2.8. And on the right plot, I fix my injection time to 0, and I just sweep over the possible readout times. So if you look at when you see something on the right side, you see a peak for both the negative and positive energy shock waves. And so one way of understanding this is that you have some of this generic kind of chaotic teleportation by size, but then you see that the peak corresponding to negative energy shock wave is higher. So you see like some contribution of the teleportation by size winding that produces this asymmetry that you get a stronger signal. I should point out also that at later times you can still get like this non-zero mutual information, and that's just this kind of interference effect that happens. So we're going to be interested mostly in looking at the asymmetry between the peaks. Any questions here? Okay. So you can ask at this n equals 10 level, how does this compare to what we know from like analytic computations? I should also mention the many little lines that I'm showing are just different normal random instantiations of my JI/JKL complex. So this is just visualizing the ensemble. You can do a computation in the double scale limit. So my co-author David Kochmeyer evaluated like this double scale limit where you instead of taking the traditional assumption that the number of fermions is much larger than the number of terms that couple with each other. So in our case, q equals 4 is much larger than 1. You have a much better limit that is more similar to our small n regime. So we have like n equals 10, q equals 4. So the first is like 10 is much larger than 4 is much larger than 1, but that's not so true. Instead, 10 is much larger than 1 is much better. So we can fix this q squared over n as 16 for 10, and evaluate what we expect from like a chord diagram computation the mutual information to be. And we get these points with error bars, and they have error bars because there's some nasty integrals involved that were approximated. But you can see that qualitatively, even though it's still not a great approximation, it gets the correct characteristics that we're seeing of this n equals 10 numerical simulation. So it's looking reasonably scaled for this like n equals 10 model. So now we want to try to get to a smaller Hamiltonian that is sparser, something that will take fewer gates to run on a quantum device. In order to create this, what we do is create some kind of analogy to a neural network. So in a neural network, you train it by back propagation. So you can take derivatives across everything. This allows you to determine your weights. The nice feature of the protocol that we're using is that everything is fully differentiable. So you can, again, back propagate across your entire Hamiltonian. So we try to match the mutual information dynamics. Nothing else. We just take the mutual information dynamics in this kind of symmetric injection readout situation. And we construct a data set out of that and say, well, I'd like you to produce another Hamiltonian that has the same mutual information asymmetry. And then we optimize the weights. These weights are the SYK coefficients, J, I, J, K, L. And we backpropagate over those coefficients in order to achieve a Hamiltonian that has the same mutual information dynamics. But when we try to find these coefficients, we apply what is known in machine learning as L1 regularization, which introduces this penalty, this lambda, in terms of the sum of the magnitudes of the coefficients, which biases the coefficients to become increasingly sparse. This makes terms of your Hamiltonian drop out. You get a bunch of zero coefficients in front of many of the terms. And if you do this enough, then you come out to only 5 terms, which is much larger than the over 200 terms that you start with. So now we want to look, do this Hamiltonian with 5 terms resemble gravity?
Sure. Is there an analytic understanding of the coefficient from other than the machine learning? In the sense, do you know like other choices of the coefficient might also give you what you want?
So we tried, but it's pretty hard to take this and then work backwards as to what it could mean. One nice feature and something that we're very curious about is this procedure naturally produces an ensemble of Hamiltonians. If you do this many times, you're going to get many different complements. And so hopefully by looking at an ensemble, you can get a better idea of like universal characteristics of what that has. But directly, it's quite hard to see exactly what's going on because, well, that's how machine learning works. So yeah.
And it's just a second number.
Fermions.
Yeah, and fermions. But here, first, slide 7, why in this
good question. So this classification tries to set as many of the terms to 0 as possible. And this can cause you to lose support over some of your fermions. So you just set all of those that would on psi 8 to 0, and now you can throw away psi 8.
But why do you go like this way? I think like compressor 1% X, that's what we have. Here you only go to psi 7, that makes no sense.
Yeah. So it is pretty odd. But we can still ask about the physics of the Hamiltonian it produced. The only guarantee that we're given is that it has mutual information dynamics similar to the original n equals 10 spectrum model. It could not look at all like gravity by other measures, and so we're going to look at those other measures now. So here on the left, I show this is the mutual information we trained it to match. In the background, although the colors are a bit faint, we have like a full ensemble of other ML models. They all have kind of similar dynamics. But you can see that we train like this green to match the purple and black and yellow to match the black. And indeed, it did its job well. And the dynamics at least look similar. We can now change up to something it didn't train and say, what if I fix the induction time instead of the readout times? And we see it actually also match those dynamics pretty well. But these are kind of, these should work because we trained it to do mutual information dynamics. So let's ask about some other physics. So the first thing we can look at is, does it show operator growth? So how does it behave at the time of the teleportation? The teleportation occurs at t equals 2.8. So here, this plot is quite a bit to digest. So I'm going to try to work through it slowly. I'm showing you the operator support on operators of different size. So I'm summing over. This is essentially from like the size distribution that I showed you earlier. I'm summing over the magnitudes of the CV coefficients. In solid are each line here corresponds to a different fermion out of the 7 fermions. So you can see that in solid, I have operators of size 3, and in dash, I have operators of size 5. So you grow onto operators of size 3 first, and then at some later time, you'll grow onto operators of size 5. In black are the fermions that we're actually going to do the experiment on. So black shows the psi 1 and psi 2, which are the 2 fermions we're going to teleport. You can see they grow relatively quickly on both operators of size 3 and 5, such that at the time of teleportation, t equals 2.8, we have some support on operators of both size 3 and size 5. Then you can ask how do the other fermions look if you want. And in red, I show 2 of the slowest growers, fermions 4 and 7. And they are the slowest at achieving some support in their operators. So they grow more slowly. All of this is at beta equals 4, which is this temperature that we're going to try to do the teleportation at, that we looked at the SYK model. And so we can see at least that our model is showing operator growth. And also similarly, if you were to plot the 2-point function, you would see that it decays on a single-sided system by t equals 2.8. So at the time of teleportation, we have this kind of growth and decay of 2-point function that we should expect. Any questions about this? I apologize for the number of lines in this plot.
Just make sure. So the machine learning, the training show that you only need 8 Majorana fermions.
We ended with 7. Yeah, 7 in the end.
8 to be.
Yeah, if you
8 to the proper
exactly
integer qubit space, right?
Yes.
Dimensional qubit space, but in that case, there are 2 to the 4s. You'll say 2 to the 4 will be 16 instead of 2 to the 5s.
So here I'm looking at how the operators grow. So we take psi 1 and psi 2, these just by psi 1 and psi 2 span hyperspace dimension 2. And then by the time they're on operators of wider support, they grow to grow in this space of dimension 32 to 5, where with operators of size 5, we have 2 fermions, psi 1 and psi 2, each support operators of size 5. Then you can also ask about a counterfactual scenario and say, well, what if I continued evolving past the time of teleportation? How do my dynamics look? Well, if you were to choose the evolution under each of the single-sided systems, HL and HR, then because the Hamiltonian has commuting terms, you don't get thermalization. You're going to get some recurrence because everything here commutes. And so at later times after teleportation, even though we saw like a 2-point function that decayed and operator growth, as you go later and later, these will have fluctuations. Your 2-point function will go back up from decaying, and you'll get non-thermalizing behavior at late times. So this is one kind of way you can extend dynamics past the event of teleportation. Another way to do it is by evolving under the eternal wormhole Hamiltonian of Maltese energy, where this V over here is again our kind of interaction Hamiltonian. And from the gravity story, we expect this to thermalize at high temperature. And indeed, it does because V does not commute with HL and HR. And in fact, if you took this Hamiltonian and you asked about trotterizing it, the normal thing we do in quantum simulation, if you evolve under that Hamiltonian, this one trotter step under H total is exactly equivalent to the circuit that we run in the teleportation protocol. So the Hamiltonian that you choose to extend the count this like dynamics after teleportation if you change the Hamiltonian, you can get dynamics that look more or less gravitational. But at least we're seeing that the coupled system of the total Hamiltonian does look gravitational. In fact, if I look at this coupled system and I ask about how the 2-point function at high temperatures behaves, you find that it decays for all the fermions as we'd expect from thermalization. And we can look at how fast each of the fermions decay. So again, the black ones are psi1 and psi2, and the red ones are psi4 and psi7. Psi4 and psi7 were the slowest to see single-sided operator growth. They're also the slowest to see thermalization under the eternal traversable wormhole Hamiltonian. Here, I'm taking high temperature. At low temperature, we should expect large oscillations because the ground state of this coupled Hamiltonian is a TFT state. There should be an O of 1 gap. So we should see oscillations, but at high temperature, this is what we expect in gravity and is what we see. So how do you interpret these kind of decay rates? Well, the most direct holographic interpretation is that the fermions shown in red are less massive. They have like a spread out wave function, and they fall into the wormhole more slowly as a result of this. So why are we interested in asking this question? Well, it turns out, if you look at the size winding, that you get some interesting behavior. So I mentioned earlier that this winding size distribution, Q of L, should have phases linear in L. So on this right plot, I'm showing those phases and the size, and you can see that all these fermions have phases linear in L. So this is the teleportation by size winding. But these lines I'm showing you are at different times. So I'm asking at what time does this fermion achieve its best size winding? When do these phases look the most linear? And I measure linearity by taking like the standard deviation of the differences between points in this line. And I just scan over all times until I find the time of best size winding. So you can see eventually all reduce the size winding, it should teleport. But the time at which that occurs changes. And in fact, if you look at it compared to how fast the eternal traversable wormhole Hamiltonian's 2-point function decays, where I just like check its value at t equals 3.8, you see that there's a linear relationship here, that as you decay more slowly, so your 2-point function has a higher value, the time at which you'll achieve size winding is later. And so this is actually, I think, a signature that we did not expect at all. Because if you just look at, let's say, the size winding at time t equals 2.8, you would find that some of the fermions don't have great size winding. It turns out, though, that they have much better size winding if you just look later. And so this is consistent with what we would expect from gravity, where if you're falling into the wormhole more slowly, you have less mass, you should not be able to teleport across until a later time. So you should have size winding at a later time, which is exactly what we're seeing. Are there any questions about this plot? Okay. So I can show you, in fact, the mutual information for those fermions in red, psi4 and psi7. These two fermions have the worst size winding at t equals 2.8. Yeah, go ahead.
Size winding here. Not sure.
Sorry, so
Is it the winding?
sorry, so let me go back to the definition. That should help. So you achieve teleportation by size winding if this distribution here has magnitude similar to size distribution and is linear in the phases. So here I'm just asking, when is it most linear? When are the phases most linear in the size? And I'm going to call that your time of best size winding. And if you work through them, the mechanism, you see that ansatz is enough to produce teleportation. So the measure of size winding in my plot is just how linear in size are the phases of Q of L. And I'm not used to it, so I'm going to make it.
Your blog on the screen.
Oh, okay, sorry. Let's try. Does that answer your question though? So I'm looking at, yeah, the checking that these are linear in size. And these are plotted at the time when they're most linear in size. And that time correlates very nicely with how fast things fall into the wormhole. So we can take fermions 4 and 7, which have the worst size winding at t equals 2.8. But those fermions we also saw with the slowest to thermalize and the slowest have operator growth. So if we instead take them like from here, we should see that around t equals 4, if I pair up those two fermions and apply the teleportation protocol to them, they should be able to teleport by size winding. And indeed, we see that we have this nice asymmetry in the peak where mu equals -12 here in blue shows a stronger teleportation signal than mu equals +12. So the kind of fermions that are the worst at t equals 2.8 do indeed show teleportation by size winding if you just apply the teleportation to them at the right time. But let's go back to our experiment where we looked at fermions psi1 and psi2. Here, because it's easier to just look at one fermion at a time, we can show you psi1. So we want to ask, is the sign of the interaction correct? Is the magnitude of the interaction correct? This size winding distribution, I show you here in spaces again over the sizes. At t equals 0, you see it quite steep, and then it eventually moves towards the horizon. And before the interaction, the phases are still linear in size. And then after you apply the interaction, the slope flips sign. And so this flip of sign of the slope does correspond in the bulk picture to crossing the horizon, because you can relate this distribution with the bulk position by taking the Fourier transform. And so we confirm that we're moving in the correct direction and that we have strong enough of an interaction in order to actually achieve this gravitational story. One remarkable fact, to me at least, is that machine learning didn't know about any of size winding. We just asked it to create asymmetric mutual information. Instead, this mechanism kind of emerged as the easiest way for it to create the asymmetry in the interaction sign. And so that is quite exciting to see that it landed upon the size winding mechanism as the most natural way to teleport. We can also look at what the other signatures we discussed were. So here is far too much information on one slide. On the left, we look at the causal time ordering. So this is what we expect for the expectation that if you throw something in earlier, it should come out earlier. Something in later, it should come out later. Because we need causal time ordering for a space-time description. So here I show you two kinds of scenarios. One is the protocol we run. And here a negative slope means you're causally time ordered. A positive slope means you are time inverted ordering. You can see that there's a window where it looks slightly more time ordered. And this is consistent with the fact that we still see like a peak for positive mu. So we're still getting some of this kind of more generic teleportation, but that's associated with just random chaotic circuits. So we should expect like some time inverted signal, but if you have combined with it some of the gravitational teleportation, it makes sense that you will now move towards time ordered teleportation. And if you hold open the wormhole open for longer by applying this interaction over multiple times, so you send multiple negative energy shocks, you see that you can actually invert the slope. So I plotted here just at the cusp of it being inverted, where you get to time ordered teleportation that's causal. So the Hamiltonian that we learned is capable of this causal time ordering. We also said that it should work better at low temperature instead of high temperature, because size winding is this low temperature effect. So if I run the protocol at low temperature, I get this original signature. And if I run it at a higher temperature, the teleportation mutual information is lower, so it works less well. And that's consistent with our expectation that size binding should only be working at lower temperature. Here I'm showing the difference between negative and positive energy shock waves. So we're just measuring asymmetry here. So it becomes more symmetric with the signal if I raise the temperature. The final kind of gravitational signature we expected was this Shapiro time delay if you send in 2 fermions. So this is the experiment where I throw something in from the left, same thing as I throw something in from the right. And we should expect them to somehow interact in the bulk, which will cause the signal to come out later and become weaker. And we see that as the case as well. The signal weakens and moves to the right. So these are just nice consistency checks that tells us that at least what is going on is interesting physics, and it does resemble gravity. So now we move to the experiment. These are experimental details. How do we prepare the thermofield double state? Well, as I mentioned earlier, the TFD state is the ground state of this eternal traversable wormhole Hamiltonian. And so we can prepare it by just variationally finding the ground state of the Hamiltonian with a variational quantum eigensolver. You basically have a parameterized quantum circuit, and you modify the parameters of those gates to try to minimize this energy. And we should see that doing this procedure produces like over a 99% overlap with the true TFD state. So it's a convenient way to obtain a shallow circuit that does this. And then to measure the mutual information, we just went for something easy. We work with Renyi entropies instead of von Neumann entropies, and just like measure over all possible polys in order to obtain those entropies. The 9 qubits that we use are shown here, calibrated with this kind of cross-entropy benchmark calibration. We throw the usual readout error mitigation tricks and applying spin echo sequences to try to prevent dephasing and other errors. And these 9 qubits here were essentially the best 9 qubits available on a Google device at the time. And although it's a small number of qubits, the key issue is trying to actually work well for deep circuits. Since our circuit is fairly deep, as you make your circuit deeper and deeper, you get exponentially more noise. And so the qubits were not the limiting factor. Instead, it was how noisy are the individual gates as we tried to do this very large circuit. So as a first test, we ran
Sorry. Did you say something about the best 9 qubits?
Yeah.
What do you mean by that? And also, can you explain this design area?
So the chip itself has order 50 qubits on it. And we want to find which are the least noisy 9. And so we can apply this kind of calibration tools to measure how noisy are the gates. So here the lines are showing how noisy the 2-qubit gates are. The dots are showing the individual single qubit gate errors. The benchmarking for this is done based on these random circuits. But with that's what they call cross-entropy benchmarking. And so we need also 9 qubits that are like in a layout that's convenient to make our circuit shallow. This turns out to be the best layout for doing that. And so the subset of the 50 some qubits in the chip that had the lowest errors for these 9 that I showed you. So as a first check in the experiment, before running the wormhole teleportation circuit, we run this kind of mini experiment to just look at the 2-point function and see if we understand the noise in the chip. So if you just swap in part of an EPR pair, evolve, and swap back out, you can measure the mutual information between P and T. And you should expect this if the 2-point function decays, you should expect that mutual information to decay. Indeed, If you had a noiseless simulation, you get this black line. The experiment has instead like this golden dots, and it's as you can see a pretty large number of order 1. Here the mutual information is normalized to go up to 1/log2. And if you take the gate errors and just plug them in and ask how much noise did we expect, well, it lines up pretty well with the experiment. But this is a very basic feature, this 2-point function. It's nowhere nearly as sensitive as the teleportation by size winding. So here's how it looks when you actually do the full, these are our main experimental results, when you do the full teleportation circuit. So on the left here, I'm fixing the induction time and sweeping over the readout times. As you do this, you get some kind of peak, but much, much smaller mutual information numbers. And that's because of how fine-grained the mechanism of size winding is. If you plug in the noisy simulation, you do indeed expect these tiny numbers to be appearing. This kind of effect requires you to essentially like spread over many operators and then unspread over all those operators. And so it's extremely sensitive to device noise. Nevertheless, we do see a peak at from the noise simulation, you can see about the right time and about the right height. The experiment where you take T0 equal to T1, so you do the symmetric induction readout, you instead see a much smaller signal, or like much more damped signals goes on. And this is because as you it gets attenuated, but it's exponential, because as you evolve for longer and longer times, you're spreading over more and more operators, and so more and more sensitive to noise. And if you symmetrically change the 2 times at either end, this attenuation hits you sooner. And so, yeah, it's less clear of a signal. And perhaps as a final note, I'll point out that try to show you like how sensitive this is to noise, how important it was to try to get the least noisy qubits possible.
Actually, sorry.
Go ahead.
Slide.
Yeah.
Can you say? Should I compare the two again? I mean, can you just say again?
Yeah. So this on the left, I'm showing the mutual information difference. So
yeah,
between negative and positive u, and I'm looking for an asymmetry, so it should be away from the 0 line. Indeed, we see a peak, but this is for this kind of experiment where I fix the induction time and scan over the readout times. Here, time on the right, time grows twice as quickly, and so it's much more sensitive to the scrambling. And the scrambling causes like an exponential attenuation. This makes the signal a bit hard to see, and we get to like 0 quickly. The device itself has like very time-dependent noise, so it's hard to get like an accurate noise model of how it works at the instant. But at least from like our calibration noise model, we expect like a pretty small peak.
But the right-hand side figure is what you prefer to see.
The left and right are just like 2 sides of the same coin. We're just looking for this asymmetry in mu, and so we're happy to see either signature here. Yeah. I don't know if that's what you're asking.
I just want to make sure where we read the dynamics. Is that a peak you are looking for?
Yeah, a peak in either plot, or both plots.
Okay. But I say the peak on the right hand side is probably greater to be seen compared to the left hand side.
I don't think one is necessarily better or worse than the other, because we're trying to check if it's teleporting by this mechanism that just does depend on mu, where mu negative should cause better teleportation, and either plot would reflect that. So, yeah.
Thanks.
So how sensitive are we to noise? Well, if we reduce noise by a factor of 2, we would get a signal that's 10 times larger. If you increase noise by 50%, the signal would be completely obliterated by the noise. So this just says like how sensitive size winding is, because of this delicate operator growth and like alignment phases. So if we had used the Google device 2 months earlier, we would not have been able to see the signal. It is really at the edge of what was experimentally possible. So we're very excited to have seen the peak. few comments on future directions to close out the talk. So we're trying to, this was like a first step. It's a thing you could have done on a past computer, but it is a step towards actually doing this quantum gravity in the lab. To see things that are with stronger gravitational signatures, you could try to make the model less sparse. That could make its dynamics more robust in general. You can also try to increase n, where you can then access more delicate observables and do more interesting, maybe scattering experiments and so forth, where you can learn more about gravity. In this larger n, probably the most interesting regime is somewhere larger than what classical computers can do, but smaller than like the actual analytic large n regime. In this kind of mesoscopic area is the area where you can expect a quantum advantage for classical computers to teach us something about gravity that we can't otherwise evaluate. And so there are many questions that one can think about that would give you some clues towards how this kind of not like small n effects, but not so small that you could run on a classical computer, what you can learn from there. There are also other interesting, from an experimental view, other interesting quantum platforms you could try to run, because the SYK model is kind of inherently this all-to-all connected thing. Superconducting qubit device is not necessarily the most natural thing to use. It has locality and force. And so if you want an interaction between two distant qubits, you have to do many, many gates, a lot of noise. And so if you use something like a neutral atom array, where you can move your atoms around and do interactions without causing so much noise across your gates, then that could also be a very natural platform for doing an experiment. So there are many directions to look at this theory experiment, and we find this very interesting. Thank you.
Thank you very much. Thank you, Alexander. Any questions? Comments? Please. Let me speak louder. Yeah.
You just expanded that theoretical
and maybe also repeat the question. You get a question?
I think I heard most of it.
Because for the audience,
so the question is about what kinds of things we can learn on the theory side by going to like larger n and stuff like this. So one thing you can definitely try to do is ask about like more fine-grained scattering experiments in the bulk. You can send in different sorts of excitations and see what comes out. You can also ask about like what happens if you didn't quite initialize in the TFT state, you initialized with some other perturbation of the TFT state and ask how this changes your dynamics. So the questions that are like the most interesting from the perspective of why you use a quantum computer are those where you can maybe see like some of these string corrections that you would expect at a fairly large and larger than what a classical computer can do, but not in the like fully semi-classical large n limit. If that answers your question.
Any other question, comments? I think before the talk, you said you would answer my question about the comments on your paper.
Yeah, so I think I touched on the like the size winding and stuff like this.
Okay. Maybe just summarize again. You can.
Sure. So I guess we were talking about like at the time of the teleportation, you do see this operator growth and kind of declare the 2-point function that you're looking for. At later times, you can ask about different counterfactual scenarios. One is extending the single-sided systems. One is doing this like eternal traversable wormhole Hamiltonian. And you see thermalizing dynamics in the latter. Perhaps also the size winding, although it's not necessarily required for all of the fermions to show size winding because you could have non-gravitational interactions in your model. We do see, in fact, that all the fermions have quite good size winding. They're good enough to allow them to teleport for size winding. But the time of size winding is clearly related to like the the rate of decay of the 2-point function. And so it seems to actually lend itself to an even tighter kind of interpretation where you associate different masses to different fermions. And this is quite consistent with the behavior we see.
Okay, thank you.
Thanks, Ken.
Any more questions? No. Okay, now let's thanks Sandra. Yeah, thank you. Good, actually. Also ask the online. Thank you. But if there are some people have a question, comments online, you can also ask.
Comments.